Gilbert Lewis, whose name belongs to Lewis dot structures, examined Bronsted and Lowry's definition of acids and bases from a different perspective, that of electron pairs. We'll begin by looking at several conjugate bases. One of the things that Lewis noticed about the bases is the presence of these electron pairs that could be donated to other species. Hence, that's how he began a definition. Lewis bases are capable of donating electron pairs. Now, what did they donate it to? Well, according to Bronsted and Lowry, we had to focus here on the proton. And the proton was capable of accepting pairs of electrons. But Lewis expanded that because there were other things that could accept electron pairs, perhaps positively charged ions. And also, compounds of boron were capable of accepting pairs of electrons. And we'll look specifically at those in our next slide. But let's first look at how ions are capable of accepting pairs of electrons. Here I have the sodium ion interacting with some water molecules. And those electron pairs would be attracted to the positively charged sodium in what we call a coordination bond. Now, there can be up to 6 water molecules that could surround a particular sodium ion. So here's the equation to represent that. Sodium acting as our Lewis acid, accepting pairs of electrons, and the 6 water molecules donating their pairs of electrons. And they would form this complex ion. Let's look a little bit more at metals and ions in water. So again, I'll begin with my sodium ion with attracted to 2 water molecules. It has the following equation, which we've seen before. How does that differ, say, with interacting with an iron ion? Well, first of all, iron has a greater charge. That would allow it to draw the electrons closer. This would then cause the water molecules that are surrounding the iron to become bunched together, and this can sometimes result in the release of a proton. This is what Bronsted and Lowry were looking for. Here's the equation for what goes on. So the iron forms a complex iron ion, and as those water molecules are drawn close together, a proton is released. This would cause, in comparing the two, the sodium in water remaining neutral, whereas the iron compounds in water would become acidic. Metals that are small and have high charges tend to hydrolyze water, producing this H+ ion. Now we'll look at what makes boron compounds unique. Boron, if you can remember from our look at shapes of molecules, tends to have 3 bonded pairs of electrons. It's too small to easily accommodate 4, but it can accommodate up to 4. Here, ammonia is capable of donating an electron pair to the boron to complete its octet. And we would represent that this way with the arrow indicating, again, a coordinate bond. Let's look at a couple questions on this concept. First of all, which of the following reactions represents an acid-base reaction from Lewis's concepts, but not according to Bronsted-Lowry? Remember, Bronsted-Lowry are looking at proton movement. And if you examine the 4 options that are available, there's only one equation that doesn't have a movement of the proton. It remains, and that would be in C. In our next question, we're asked to arrange aqueous solutions of the following metal chlorides from lowest pH to highest pH. So let's begin by establishing a spectrum here. First of all, with the lowest pH, that would be the most acidic. So we're looking for something that has a high charge and a small radius. That would be my aluminum with a +3 charge. And conversely, if we look at the other end of the spectrum, the highest pH, or closest to being neutral in this case, the KCl, with potassium only having a +1 charge. The remaining 2 compounds both have a +2 charge, but I'm going to now look for the one that tends to be smaller of the 2. And zinc, having more protons in its nucleus, will essentially be a smaller species than the calcium. So it would tend to be more acidic, whereas the calcium would fit the gap. Lewis acid-base theory fits Bronsted-Lowry theory by changing the emphasis of acid-base reactions from the proton to lone pairs. It broadens the field of potential application. This is how science works. Thanks for watching.